Hey, what's up, everyone? It's Alan back for 1.1, the actual first section of this review chapter. So we're going to talk about functions in depth, just give you a bunch of definitions. So I'll run through these, but what I would like you all to do right now is pause it, go through this entire section, see how much of this you can actually fill in, think about it, go over it, rather than just copy it down and not actually work that brain out. So do me a favor, pause it, try to fill out and go through as much of this as possible. Then I will come back, give you some of the things that need a little bit more explanation. Otherwise, give you the fill-in blanks and continue on with reviewing of functions. Go for it. All right, hopefully you gave yourself a chance to go through all these, think about them, and even come up with most, if not all of them. Just going to run through these real quick. Lots of definitions in this first section here. So without further ado, let's get to filling in these blanks. Function f consists of a set of inputs and outputs. We call these the domain and range. For every x that we put in, that's going to be our domain, like our home. Everything that comes out will be the range of values that we get. All right, hopefully that's familiar. You're able to come up with those on your own. Definition 112 means it's from chapter 1, section 1, second available definition. The independent variable is typically denoted by the variable what? What do you think is independent of anything else in that? The independent variable is typically denoted by the variable blank. Which one is independent of all the others? That's our x. Therefore, the dependent variable, we use y or f of x. And together, they form a relationship where every input value maps to exactly one output value. So I like to think of this as a vending machine, and if you were the owner of this thing, you would want to make sure to maximize your profits, that it functions properly. Therefore, if you wanted it to operate, whatever somebody put in, of course, the money first, they put in A7, then for it to function, you would want whatever you were trying to select with that A7, that's what you would want out. Okay, so same type idea, that independent variable, independent because you could choose anything, we put into that relationship we call a function, and something, one thing will come out, the thing that we wanted. Right, so functions we know are typically written as, instead of just the y value, we write f of x to let us know that in that function, we're going to put in some x, and that's what we will get out of that function, that f of x or y value. And it is therefore called function notation. All right, there's a couple different ways that we can write these relationships. All right, one is called interval and the other set builder notation. So let's review them very quickly with a few definitions here. Chapter 1, section 1, number 3 and 4. Set builder notation. You basically just give me the set by these curly braces and tell me this right here means such that. Here's some x such that x has some property, like 2x plus 3. All right, so that would be our example of the relationship or property that x is having. We can use this in many different ways, but that's just one. The one that we use most often is that interval notation, where instead of saying that there's some property for our x, all right, we will say instead of x being less than or equal to 3 and greater than 0, we can make that much simpler and just say, well, it's from 0 to 3. And then we just got to make sure, is this included or that, or is it just everything in between 0 and 3? And that's why we use what is called the interval of numbers with either a parenthesis or a bracket. The first thing, the way that we read from left to right, the same way that we read on our number line. So it would be A here and then B there. When we did these, you'd put open dots or closed dots to represent including B and excluding A, but everything in between. Usually would just do this to let you know. or if it was outside instead of inside values, right? So hopefully you remember that. The one key thing you want to make sure is that open dots have that open parenthesis, where closed dots have that bracket. Okay, so hopefully that will help you to remember those two blanks not included in the value. We use a parenthesis, either that or that. If it's including, then we will use a bracket. And remember, it can be one and the other within our interval of values. All right, so we will use these frequently. And we also want to talk about how we know whether something is a function given its graph. So here's a few more definitions for you. Definition 115. What are we talking about here? How do we tell if a graph is a function? Well, remember, in order for something to function correctly, one input, one output. And in order to test that very quickly, we use a little thing called the vertical line test. We literally draw vertical lines on the entire graph, and for every one of those x values, we would see, does it hit up here, 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 down here? Is there only one value, or is there more than one? Because if it hits more than once, then that's not functioning properly. We need that one value for each and every one of our x values that we're testing. Right? So that is what is called the vertical line test. Right? So you can use an app called GeoGebra. There's also Desmos, graphing calculator, anything you want to do to kind of mess around and manipulate those things. Once I send this to you all, you'll have that hyperlink so that you can actually click there. Don't try to do it right now on this recording. And it will allow you to manipulate various functions and play with that a little bit to understand it a little bit better. All right, some other things we want to talk about with functions is whether they're increasing, decreasing, or even a constant over some interval or length of numbers. How would we do that? Take a look at these definitions, 116, 7, and 8. A function touches the x-axis when f of x equals what? So before we get to the increasing, decreasing, and constant, we want to talk about one special case. When we get what is called a 0. When our y value is equal to 0. What does that mean? Well, graphically, we know if we had, say, a parabola like this, it would be a 0 there and there. So we call these, because of how we find them, by setting the function or the equation y equals to 0 and solving for those x values where that would happen. And because graphically, what that provides for us is called an x-intercept. So hopefully you can see that these are obvious why we call them that. The 0 because that's how we find where those are located, and what they give us graphically are indeed where it intercepts the x-axis. So now that we know that, you can see as we read this from left to right, it is decreasing. And by it, we're talking about the y values. We usually count from left to right increasingly for our x values. So what we're really comparing are the y values. And remember, y is equivalent to the f of x. So if we have just 2 points, let's say x1 and an x2, and let's say we went here for x1 and over here for x2, well, x2 is typically going to be the one that's the larger, obvious reasons. 2 is greater than 1. So then what is happening to their y values? Which one would be bigger? Well, as you can see, the x1 would be the smaller value for y, and the x2 would be the larger. So what's happening as we go from left to right? For that example, well, they would be increasing because my y value went from a smaller to a bigger value. But would it be doing that on this entire parabola? No, not for this function. If you went over here and said that this was your x1, and here this was your x2, now look and see that this is bigger and this is smaller. but then that tells us that they are decreasing. So taking a look at this, what does it mean when our x1 is less than x2 and our y value for x1 is greater than the bigger x value, x2, its y value? Well, think about this again from left to right. X1 is here, x2 is here by definition. But what is this saying? Our x1 is going to be a bigger value. Our x2 is the smaller value, which means it is decreasing on just that interval we're going to call capital I. For all those values and in between them, and this symbol right here means that it's an element of, or in easier, simpler terms, inside of I, that interval. So the next one, again, x1 and x2, this is the smaller of the pair. So looking at that, x1 here, x2 here, but this time it's saying that f of x1 is what to f of x2? This time they're saying smaller. Doesn't mean it's negative and positive. It can be this scenario, but you can see that it's definitely what? Hopefully you said increasing. Again, on that interval between x1 and x2. Now there is a scenario where it's not doing either increasing or decreasing. There can be a time when we say that they are actually the exact same. And if they're the exact same, then that means for every x1 and x2 and everything in between on that interval, what is happening? If they are the exact same y values, then that means we have something like this. That and everything in between gives the same y values. So it's constantly going to be the same, and therefore we call that a constant function, at least on that interval. A few more review problems here that we want to talk about in this first section of chapter 1. Not going to count the 0, which was just me adding on some basic stuff. We'll also use this increasing and decreasing for this thing called concavity down the road. All right, but before we do, we're going to be talking about a few more things, like what else can we do with functions? We can have one function that is composed or made up of another. So rather than just putting an x into our function and seeing what comes out or results, we can put an entire function into another function. So the way that we read this is we say it's g of f of x. So just like before we would say it's f of x, now we're going to rewrite this as g of what? Well, a whole nother function. So instead of just putting a simple number or that unknown variable we're using as x, we can put an entire function in place of all of the x's into this other one we're calling g. You guys should be familiar with that. Just get rid of that weird little o, which is short for of. You may or may not have heard of symmetry before, but I wanted to quickly talk about this, even though we won't use it a ton, but it will come in handy a little bit more in second semester of calculus, a little bit towards the end of this one. There are two types of symmetry that we will see and deal with, but not all that much, which is why I'm going to quickly just introduce it and then we'll move on. There is symmetry about the y-axis, and then there is symmetry about the origin. Of these two, which one is which? Now, I know it's a little deceiving because A has this one and B is, but of these two graphs, which one has symmetry about the origin and which one has symmetry about the y-axis? So let's start with the first one here. Which of these two has the symmetry about the y-axis? Well, hopefully you can see if you just drew that vertical line right there, all of this would fold over to the other side and line up perfectly. So this one actually is the one that has the symmetry about the y-axis, which means you can probably guess part B, the one that has symmetry about the origin. Now remember, where we originate from is 0, 0. And so what does that mean? How do these different symmetries work? Well, if I went right one and left one, so I did the opposite. Here I went 1, here I went -1 for my x. Notice what my y values, the outputs would be for those. Here and here, they would be the same, that -4. You can punch it into here, both the +1 for the x and the -1 for the x. Work this all out and you would get the same value. But what if I put in 1 here and -1 here? You can definitely see that they are going to be different. But how are they related? Notice over here, if I did it, I'd get a -3. But if I put the -1 in, I ended up with +3. So how are they related when it's symmetrical about the origin? Whether you're putting in 1 and -1, in either of these, here you get the same value, symmetrical about the y-axis, where here you actually get the opposite value. So that symmetry is about the origin, same distance from there to there. Here, the distance was the same from the y-axis, no matter where we went. Right? So that's the difference between symmetries about both the origin and the y-axis. But of course, we want to make sure that now that we've seen it graphically, geometrically, how can we decipher that if we don't have a graph? Algebraically, in other words. Check out definition 1.1.11. All you got to do to test symmetries is plug in a negative or opposite of x, because what we're going to be given is the original function. So what we're going to test is the opposite values. And as we saw graphically, if we end up getting, when we go 1 or -1, the opposite of one another, if we get the same value, then it's symmetrical about the y-axis. If we plug in 1 and -1 and we get the opposite values, then we know it's symmetrical about the origin. So we're going to just name these because those are mouthfuls. We're going to say that if it comes out a negative or positive, if we put in that negative value and get back our original, or if we put in that negative and it comes out the opposite of our function, then we're going to say it is even because we got the same. Or if we got the opposite, we're going to call it odd. And if it's even, we know when the score is even, we have the same score. So therefore, we will say that it is symmetric about the y-axis. Where if it's odd, then you know we got the original function. When we put in the negative value, we got out the opposite. So that means we would have the origin as our symmetry. Okay, so some of these things, again, can help us to do things more quickly. We'll even talk about these things called end behaviors and whether it's increasing or decreasing, amongst other things. All right, keep working at it. Go practice. I'll see you in the next video.